Okay, so we have chapter 14 today. So we're going to finish chapter 14. And let's see, we might start also with chapter 15 if we have enough time. So as I have told you, chapter 14 is the most important chapter because this is the introduction of chemical equilibrium. Okay, so in the chemical equilibrium, it tells you that a reaction can be reversible. So you have reactants on one side and then the products on the other side. And what you're going to do, okay, the products that form can act as a reactants and then favor the backward reaction to form products, which initially was your reactants. Now, the concept of chemical equilibrium, although not taught directly, was already introduced to you as early as chapter 11, okay? When you have the vaporization and condensation process, wherein you have a liquid. If you put it in a closed container, so initially the liquid will go from liquid phase to gas phase. And when there's enough gas space, some of this would start to condense until such point that the rate of vaporization is the same as the rate of condensation. So as I have told you, there are two conditions that are usually met for a chemical equilibrium to be established. First is the forward and the reverse reactions are equal. And the other thing is once you reach the equilibrium concentration, the reactants and the products concentrations should remain the same. And we have discussed some specific example of this, like this one. So initially, you have only NO2. And after some time, when you force it to equilibrate, okay, there comes a time that the concentration of both the reactants and products remains constant. And then there's also an instance where it's the N2O4. That's the only one that is present. Okay. And then you allow it to equilibrate after some times N2O4 reduce from its original concentration, forming NO2, which increase after some time until they reach the equilibrium system. Okay. And they can also be a condition wherein both NO2 and N2O4 are what we call present. And after some times, they will reach a state in equilibrium. Now, the way you express the equilibrium is just the ratio of the products over the reactants. So what K tells us is something to do with the ratio of the products over the reactant. So if you're going to look at the general equation in expressing chemical equilibrium, you follow this law of mass action. So A of A plus B of B producing C of C plus D of D. And if you're going to write the chemical equilibrium for that, it's just the products of the product. So C raised to the C times D raised to the D over A raised to the A times B raised to the B. So this is based on the law of mass action. Okay. And this is where they found out that if they look at the ratio of the concentrations at equilibrium, they would usually give you the same value as shown here. The same, if not close values with one another. And if we're going to look at how or what information we can get from this chemical equilibrium, so usually when K is more than 1, it means the reaction is favored toward the product formation, or it lies to the right, and it favors the products. Okay, so like this one. So if you have more products than the reactant, the value of your K is more than 1. Now, if your K is less than 1, okay, it lies to the left, and it favor what we call the reactants. Okay, so this is how it looks like. Yeah, Chino.
Professor, is it the same as we did last week?
I'm just summarizing everything.
Oh, sorry.
Okay. You're going, always what we call the disturbing the momentum of the class. Okay. And also, I have also mentioned last time that when you do the equilibrium, usually, okay, it can be species having the same pace, products, reactants, all of them has been the same pace. So if that's the case, you have a homogeneous equilibrium. And if you are a gas, okay, aside from Kc, which is equilibrium in terms of concentration, you can also express it in terms of equilibrium in terms of pressure. But in most cases, we know Kc is not equals to Kp. And the relationship that we have, which I want you to know, is this one. Kp equals to Kc times RT raised to the delta N. Well, delta N is the moles of the gaseous products minus the moles of the gaseous reactants. Okay? So in the homogeneous equilibrium, you only include either the gases or the one that is in aqueous. So if you have a liquid, you're not going to include the liquid because it is constant. And it's a general practice not to what we could include units for the equilibrium constant. So usually, since K is a ratio, okay, it is usually unitless. So we have discussed example like this one, and then I think we have discussed also about heterogeneous equilibrium, wherein what if we have liquid or solid in the equation. So the rule that we have is we're not going to include them in the chemical equilibrium expression. And we'll not also include them in terms of the delta N. Okay, because solids and liquids are what we call constant. So they're not included in the expression. Okay, and we also have an example of that like this last time. And I think we also solved this problem. Am I right? Okay, so did we end here? Anyone? Where did we end? Anyone?
For what?
Where did we end last week?
Oh, we
Anyone?
stopped here.
Okay. How about the others? Where did we end last time?
We ended here.
Okay, so we ended here. So this is the last problem that we have last time. So the next thing that we're going to do is what happened if we could say manipulate the chemical equilibrium. Okay, so one manipulation that we can have is what if we have a series of reaction. So for instance, we have a series of reaction wherein we have A plus B producing C plus D, and then C plus D producing E plus F. Now, what will be the chemical equilibrium if we have an overall reaction like this? Wherein we cancel out this thing. So try to think of this like a mechanism in your chemical kinetics. So the first reaction, we have K prime C. The second reaction, we have K double prime C. And if we're going to look at the expression that we have for K prime C, okay, we have this C over D, C times D over A times B. And for the K double prime C, you have E of F, what we call over E times F over C times D. So if we're going to look at the new Kc, okay, we're just going to multiply these two here. And when that happened, when we multiply them, if you're going to look at the equation that happened here, so it's just what? If you're going to replace this, C times D over A and B times E of F times C times D. And you just cancel out this one, giving you the equilibrium expression as this. So that's one manipulation that you can have. Okay. if a reaction can be expressed as the sum of two or more reactions, the equilibrium constant for the overall reaction is given by the product of the equilibrium constant of the individual reactions. So that's what you do. If you want to add two reactions, okay, the new Kc is just the product of the two Ks that of the reactions that you add. Now, another manipulation that we can get is what happens if we reverse the reaction. So for instance, the K for this reaction is this one. Now, what if we reverse the reactions? If we reverse the reaction, your products here becomes the reactants, and your reactants here becomes your products. So if you're going to look at the new K, we just reverse it, okay? We just swap the numerator with the denominator. And to get the new K, it's just the reciprocal of the previous K. So if the K value is small in one direction, okay, the K value will be big in the reverse reaction. So when the equation for a reversible reaction is written in opposite direction, the equilibrium constant becomes the reciprocal of the original equilibrium constant. Okay, so let's try to apply them here. So the reaction for the production of ammonia can be written in a number of ways. So we can rate it like A, B, and C. Now you are asked to write the equilibrium expression for each formulation. Express the concentrations of the reacting species in moles over liter. So how are we going to write the first one? So the A here. Kc equals to anyone? Hello?
NH3
So Kc is equals to
NH3 square
NH3 squared
divided by N2
N2
and H2 को keep.
H23. Right? So we could say this is a KCA, just to denote. Now, how about the KCB? So we follow what we have there. So this is
NH3 square
is it a
divided
square?
by
Is
no
it
no
a
no
square?
NH3 just NH3
Okay.
divided by N2 half
Okay.
H2 3/2.
3/2. So you just write what we call whatever the coefficients that you have here. And then the same thing with the right one, the last one, KCC. So this is just what?
NH3
NH3
2/3
2/3 over
N2 1/3 H2.
Now, what we're going to do is we're going to relate, let's say, KCA with KCB. And then we're also going to relate KCA with KCC. And then we're going to relate KCB with KCC. So what's the difference between the two, A and B? Anyone?
It was divided by 2.
This one is divided by 2. So how are we going to express the what we call the relationship between the two K? So KCA is equals to what of KCB?
KCB is 1/2 of KCA.
Is it 1/2? Or we could say it, this is the one that we have.
What? Sorry, Professor, what did you do?
I squared. Because I multiplied the 2 by all the B. If I'm going to raise this or if I multiply this by 2, what will happen? I raise everything here by 2. Does that make sense?
Yes.
By raising it by 2, I will get an expression like the KCA. Now, how do I do it on the KCA with KCC? What do I need to do with KCC?
Cube it.
You raise it to
Raise it to 3.
the 3. So when I raise this to the 3, what will happen? So this will become, okay, you multiply everything by 3. Or you raise everything to the, what we call 3. Now, how about KCB and KC, KCC? How do the relationship would look like? If we're going to express it in a simple one, how are we going to write the relationship between the two? Because you end up that this is what? KC2 and this is KC3. But is that the simplest relationship that we can get from them? So how can we express it as one as just a KC and the other one is with respect to the other one? So all you need to do is maybe KCB is 2/2 equals to KCC, which is 3/2. Because we try to simplify. So KCB 2/2 is equals to what?
1.
KCB. And this one becomes KCC 3/2. So that's the relationship between the two. So what does this tells us? This tells us that whatever we do in terms of multiplying the whole equation, what we do to the K is just to raise it to whatever number that we multiply. No, I don't want you to ask question. You're going to confuse them again. Question, Chinon.
Professor, KCB 2/2 is not 1. Like how to 1?
Did you take math? What is
Yes.
2 divided by 2?
I mean KCB is 1/2, right? You said 2/2. KCB 2/2 is 1.
KC, I tried to simplify KCB and KCC, wherein one of them is just equals to 1. How do I do that?
I mean you do
2 divided by 2 is equals to what?
1.
So what's the question? What's the problem?
But like you said 2/2, so I'm thinking that's like 1/2 times 2/2. 1/2 times 2/2, and it's not 1.
The relationship that they have here, remember, KCA is equals to KCB squared. KCA is equals to KCC third. So how do I simplify these things? I multiply them by 1/2. So when I multiply each of them by 1/2, 1/2 of 2 is equals to what? 2/2, right? Do you get it?
Maybe.
Okay? 2/2 is equals to 1. So 1/2 of times 3 will give you what? Can everyone also participate? Because I don't want this class to be hijacked by one student. You have the same right as that student. So please. Everyone gets this one. Why I end up with KCB 2/2 equals to KCC 3/2.
Yes,
Yes.
we can.
Okay? Because I'm not going to talk about math here. Please don't hijack the class, okay? You are not my only student. So, the what we call the summary that we have here in this relationship, whenever we have, okay, a given, let's say KC prime, if you're going to multiply it with a number, you're just going to raise that KC, their KC by whatever number that you multiply. Okay? So for this one, okay, you see here when we express this in equilibrium expression, it's 1/2, 1/2, and 3/2. So if we want to what we call make it similar to the first equation, all we need to do is multiply everyone by 2. And by multiplying it by 2, we raise the expression that we have here by 2. So the same thing here. So we have 1/3, okay, plus 1, and then 2/3. So if we want it to be the same as that one, so all you need to do is we multiply everything by 3. And in doing so, the equation or the expression that we have here is we raise it by 3. Is that clear?
Yes.
So whatever you multiply here, you raise it to the given expression. Okay? Now, let's go to what we have discussed so far. So, in writing equilibrium expression, the concentration of the reacting species in the condensed phase are expressed in molarity. In the gaseous phase, it can be concentration expressed in molarity or pressure in atmosphere. So here, you have to know when one is Kc and when one is Kp. And this only happen in what phase? Anyone? In what phase does Kc and Kp exist?
Gas phase.
Gas.
Gas. Very good. Okay. Now, whenever you have a solid, a liquid, or solvents, they do not appear in the equilibrium constant expression. And the K value is usually unitless. Okay, if you have a K value, it is what we call unitless. And in quoting a value for the equilibrium constant, you must always specify it in terms of the balance equation and the temperature. So remember here, we express it in terms of the coefficient that we're given. Okay? And each what we call K value refers to a temperature. What does it mean? When you change the temperature, your chemical equilibrium constant also changes. Okay? Now, if the reaction can be expressed as a sum of 2 or more reactions, the equilibrium constant for the overall reaction is given by the product of the equilibrium constant of the individual reaction. So that's just what we call the manipulation that we had. Question? Any question?
Can
Class?
you go
Yeah.
over number 5 again, Professor?
So
Just
number
elaborate.
5 is just you have, let's say, I'm going to get the whiteboard. So let's say I have this reaction. So let's say you have a question. So what is the K value that you have? Because if you're going to look at the equation here, so you have here this one, you have this one. So your K value there is just equals to K1 times K2, which is equals to 10 times 20, which will give you what? That's
200.
Is that 200? Is that 200?
Yes.
Okay. Now, what if we have the what we call reaction like this one? So how are we going to what we call solve this problem? Anyone? How can we end up with this value here, with this equation here? So what do we need to do?
We can reverse the reaction for
Okay,
the
so
second one.
Reverse
Yeah.
this one, so we'll make it C over D. And what will happen to the new K here?
That'll be 1/20, the
It will be
reciprocal.
1/20. So your new K now will have 10 times 1/20. So this is now equals to what?
1/2.
0.5. So that's the thing that you can do when you combine those manipulating stuff that we did. Question. So do you think you can get questions like this? Your exam is in 2 weeks.
So it's not gonna be on the 23rd?
No, it's not on the 23rd, it's on the 30th.
Okay.
So question? Question, anyone? Chino, you have question? Any question? Okay, so we will continue with the next one. So this one, it's just showing us the relationship of K or the two Ks, the small K and the big K. So when we're talking about the small K, it's the chemical kinetics. When we're talking about the big K, it is the chemical equilibrium. So let's say we have this reaction, A plus B producing AB squared. And you're given here that it is a reversible reaction. So Kf is equals to Kf times A times B squared. So that's the rate of the forward reaction. Now the rate of the backward reaction, since this is reversible, you have here AB2. Okay. Now, since they are in equilibrium, we could say the forward and the backward reactions are the same. So how are we going to get the equilibrium expression from this? So we can replace this one with the expression that we have here. And what we're going to do is we put on one side the ratio of the rate, the ratio of the forward reaction over the reverse reaction. And then that is just equals also to your Kc. And if you're going to look at the Kc here, if you're going to write, so this is what? Product over the reactant. So you have an expression like this one. Okay. Now, do you have nothing to remember this one? I will not ask question like this, but it's just like asking you what would be the equilibrium expression if you're going to write based on this reaction, and it's just like this. Now, the next thing that we're going to do is the so-called quotient. How is quotient different from equilibrium expression? Quotient is just the same as equilibrium expression. The only difference is quotient can happen anytime during the reaction. Kc only happen when? Anyone? When does Kc only happen? Kc only happen when?
During equilibrium.
During equilibrium. Okay. The rest, if you want to look at the ratio of the product over the reactant, you have the what we call QC. Okay. Now, what is the relationship with this? How do we what we call express the relationship between QC and Kc? Okay. So if we're going to look at the relationship between the two, it has something to do with the ratio of the product over what we call the reactant, or it tells us what condition do we have, okay, to at least reach the equilibrium. So those are the information that you get knowing the QC and the Kc. So in first instances, if the QC is less than the Kc, you want the system to go to the forward reaction. You want the system to go to the formation of products. So if QC is less than Kc, for the equilibrium to reach, you want it to go from left to right, shown here. Now, if QC is equals to Kc, then you have a system at equilibrium. And then the QC greater than the Kc, like the one here, so you want the reaction to proceed favoring the backward reaction to give you QC equals to Kc. Now, usually we use this reaction quotient based on the initial concentration. Okay. So for instance, this one. At the start of the reaction, there are 0.249 moles of N2, 3.21 times 10 to the negative 2 moles of H2, and 6.42 times 10 to the negative 4 moles of NH3 in a 3.5 liter reaction vessel at 375 degrees Celsius. If the equilibrium constant for the reaction is 1.2 at this temperature, decide whether the system is at equilibrium. So if it's not, predict which way the net reaction will proceed. So what do we get here? What do we need to calculate? Anyone? What do we need to calculate?
We need
to
to,
calculate
if the reaction quotient is equal to 1.2 or not.
Okay, so we want to see how QC is with respect to Kc, which is 1.2. Now, what's the first thing for us to do? Are we going to use this number that we have here as it is? Remember, you have here what? Moles. And based on the summary that we have, you want the concentration to be expressed in molarity. So the first thing that we're going to do is maybe convert each of them. So N2 would have 0.249 divided by 3.50. H2 would have 3.21 times 10 to the negative 2 divided by 350 or 3.50. And last but not the least, 6.42 times 10 to the negative 4. You have it divided by 3.50. Now, do you know why we're doing this? Anyone? Chino? Do you know why we're doing this? Why are we doing this? Dividing it everything in 3.5 liters. Because we need it to be in
Molarity.
molarity. Now, once we get this value that we have here, then we can proceed with getting the QC. Now, if you're going to look at the QC, it's just the same as the KC. So it's just NH3 squared over N2 times H2 to the 3. And all you need to do is replace it with whatever answer that you get there. So for NH3, it's 6.42 times 10 to the negative 4 divided by 3.50. And that would give you around 1.8 something. And this is what? Raised to the 2. And this one, N2, that's 0.249 divided by 3.50. So that's 0.0711. Do you follow me, class? I hope you have your calculator. Nothing will happen if I just do everything here on my own. Okay. So do you know where I get the 1.83 times 10 to the negative 4? Do you know where I get the 0.0711, class? Hello.
Yes.
Well, no for me.
Huh?
No.
No. We get it when we divide each of the mole with 3.5. Because we need to get the concentration. And concentration unit is moles per liter. All we need is a moles and all of them in a volume container, which is 3.5. And the H2 that we have here, okay, that is equals to 9.7 or 9.17 times 10 to the negative 3. And we raise it to the third. So again, do you know where I get this number?
Yes.
How about the others? Class, how you perform on the class is based on how you perform in this lecture discussion that we have. Okay? If you just turn on and you don't listen, or if you're just listening, you're not using your calculator, then everything will be just the same as your first exam. And I don't know if most of you are happy with your first exam. Okay? So these values that we have here, we get it from those values when we divided the given moles with 3.5 liters. And what's the value that we get? Anyway, what's the QC value that we get? So you get 0.611. Now, what can you say about that value? What would be the relationship of QC with KC? Less than, more than, or equal to? Okay, it is less than.
Less than.
So what does it says? If it's less than, which one is favored? For which one you need to do so that the reaction will reach equilibrium? which reaction should be favored? Okay, since this is less than, you need to put the reaction from left to right. And in doing so, your QC will be equals to KC. Question? Anyone? Question?
So I basically know how you guys. You basically divided everything by 3.5.
Yep.
That's how you got the second part QC.
Yep. Because remember, the one that's given to you is in moles. And you want everything in your equilibrium constant or quotient constant, okay, or constant to be in molarity. So you're
Okay.
given there the 3.5. That's why I'm trying to show you here, making sure where you get this number.
All right. Thank you.
Question? So what do we need to remember when we do calculation with equilibrium? Yeah, the reaction needs to go from left to right so that the QC will become equal to KC. Okay. Now, what we have discussed so far is just if everything is bigger. Yeah, if it's bigger, I mean, if what we call QC is greater than KC, then the reaction should be able, the backward reaction for equilibrium to reach. So what we have discussed so far is what if everything is given? And all you need to do is determine what? The QC or the KC. But what happened if you're only given what we call the initial concentration and you are asked to determine the K value or at least the concentration of all species when they reach equilibrium? Okay. So far what we have, the discussion that we have is, okay, we have the concentration either at equilibrium or at other what we call concentration or at other condition, like when we get the previous problem, we have the QC. Now what happened if you're just given the initial concentration and you're given the KC, but you are asked to calculate the concentration at equilibrium of each of the species involved? How are we going to solve that problem? And this is the type of problem that we ask during the exam. Okay, so the first thing that we do is we express the equilibrium concentration in all species in terms of the initial concentration and a single unknown X, which represent the change in the concentration. So remember, this is now wherein you're just given the initial concentration. And you're going to ask what will be the concentration in equilibrium. Okay, so you have here an X. And then the next step that you're going to do is write the equilibrium constant expression in terms of the equilibrium concentration. Knowing the value of the equilibrium constant, which is Kc, you can solve for X. And once you solve for X, you can calculate the equilibrium concentrations of all species. Let's try. So you have here a mixture of 0.5 moles H2 and 0.5 moles I2 placed in a 1 liter stainless steel flask at 430 degrees Celsius. The equilibrium constant for the reaction H2 plus I2 2HI is 54.3 at this temperature. So calculate the concentrations of H2, I2, and HI at equilibrium. Now, this problem is the so-called ice problem in general chemistry too. But usually, since I'm an Asian, I usually call this the rice problem, R denoting the reaction. So I have here H2, okay, plus I2 producing 2HI. Now, what is I? Anyone wants to guess what I means?
Initial concentration.
Okay, so I represent the initial concentration. And if you're going to look at this, you have this one. But is this the one that you're going to write? Or you're going to divide it with some other number?
Liters.
Okay, so you're going to divide it with 1 liter. Because you need to express it in molarity. Now, if you're going to look at this, if you're going to what we call, since it's over 1, so you could just say that this is just 0.500, but you're going to put there. What is our concentration of our HI? Anyone? Based on the statement there, what is HI value? Do we have any HI in the first place?
No.
No. So we're going to write what number?
HI squared.
0. Okay. Now, before we proceed, what is the QC for this? What will be the value of the QC? Anyone?
Should be
QC is equals to?
KC.
Anyone?
0.
0. Because this is just what we call 0 squared over 0.5 times 0.5, right? 0 divided by a number will give you a 0. So what does it mean here? QC with respect to KC is what? Less than. So that means the reaction need to proceed from left to right. So what is, okay, so we have the initial concentration already. So what is C? Anyone? What does this C means?
Change in concentration.
Okay, C is change in concentration. So here we put the X. So what happened to the reactant? Is the reactant increasing or decreasing? It decreased. So that means it decreased by a certain amount. So that certain amount is represented by X, and we put here minus X. Everyone got the sense why is it minus X?
Can you please repeat, Professor?
Okay. So since the reactants are usually what? Decreasing with time. So that means some amount of the reactants are used up. We represent it as minus X. The reason why we use it as minus X, because that's the amount that was used. That's the amount that was removed from the reactant. So that means at the end, your concentration of the reactants will be less. By how much? By X amount. Now, since the reactant is being reduced, what do you think happened in the product? Will the product increase or decrease? Okay, so the product would form, so that means it will increase. Now, how much of the product is formed? So we just use it plus 2X. Why 2X? Anyone?
Because 2HI.
Because of 2HI. So whatever the number of your coefficient here, that's the number that you're going to put. Now, why it is I didn't put anything there? What does the number before X represent here? Anyone?
Just 1.
1. Okay. Because what you have here, you have 1H2 reacting with 1I2. So that means you are reducing it by 1X. minus 1x minus 1x, but if it's 1, we don't usually put the 1. It's understood that if we have an x there, that means that's 1x. And then the 2 that we have here, why is it 2 is because there's 2 HI that form. And why is it plus is because that's the product. Everyone knows that. Because this is the most important part, the way you set up. And usually it's a 20 points question. So if ever you mess up, at least you can at least set up the rice table that we have here. Now, what is the E stands for? Anyone? What does E stands for? Does it stands for Elmer?
Equilibrium.
Equilibrium.
So E stands for the equilibrium. Okay. And if you're going to look at E, it's just going to bring down, you're just going to add what you have in the initial and the changes. So this one will become what? Like that. Now, do you follow? How do we set up the table? Analyze. Do you follow? Question. If this is a 10 points question and you were able to set this up, you have already around 6 points. But we're not yet done. Because the next
Professor, I'm
thing
not following this. I'm sorry.
Huh?
I'm not understanding this. Can I ask for
Yep.
office hour after lecture to go
Yep.
over this?
So the way that we look at this, what we call the table that we have here, you just want to know what happened. Initially, what do you have? And then what is the changes? The equilibrium is just the sum of the initial and the changes. Why do you say 0.5 minus x? Because that's what happened during the equilibrium. The initial concentration that you have was reduced by X amount. For the reactant, whatever you have the equilibrium is just equals to whatever you have initially and the changes that you have, which is 2x. And what you're going to do now is to express it in terms of K. How do you express Kc here? Hi squared over H2 times I2. Or not to the, just none. So I hope you follow at least this one here. Because the
Yes, that's
thing,
like, yeah.
the next thing that you're going to do is you're going to replace this expression with whatever you can find in equilibrium. So that means this will now become what? 2x2, because that's what you have as your HI. And what do we put here below?
0.5.
So you have a 0.5 minus x for one of them, and another one is 0.5 minus x. So try to look at the setup.
I think what's confusing is the zero concentration for 2HI.
So the rice table is just setting you up to give you the expression that they have during equilibrium. Because that's the one that you're going to utilize in solving for your K. Or in this case, in solving for your X. Because K is given. What is K value?
54.3.
54.3. So what you really do getting here is you want to know how much X is involved. And once you have that X value, you can determine the concentration of each of them, because that X is equals to, for the product, 2 times of that X. For the reactants, the initial concentration minus X.
Okay.
So how do we set this up? So this is what? 54.3, you have 2x squared. And you have here, if we're not mistaken, can we express this like this one?
Yes.
Because they're just the same, 0.5 minus x. So the value that we have here is known as a perfect square. So when you have a perfect square, how are you going to simplify this? How are we going to remove the squared on this side here?
Find the square root of 54.3.
Okay, so you just get the square root of both sides. So if you get the square root of both sides, this just becomes now a 2x, and this now becomes a 0.5 minus x. And what is the square root of 54.3?
54.3.
Okay, 54.3 square root equals to what?
Just 54.3.
No,
No?
that's not the
Oh.
54.3 squared.
Oh.
7.36.
So this is
7.3.
2. Anyone?
7.36.
7.36 or 37?
Yeah, if you round it, which will be 37. Yeah.
Okay.
Oh, my mistake. Sorry.
It's the square root of that one, not the square root of the square root of that, okay?
Mistake, Professor.
It's okay. Are we done? We're not done because we still don't have the x, but we at least we simplify it, okay, preventing to do the so-called quadratic formula, which everyone will be problematic, right? So right now, I'm just telling you that the problem that you have is a perfect square in your exam. But we will have what we call quadratic formula equation later on, just to show you how it's being done. But I usually what we call prevent the student from suffering that thing. But I can assure you, some of you will still use the quadratic formula when you do your exam problem. So the next thing that we're going to do is you have to solve for x. So you have to use math here. So you cross multiply it with that one. Now you ask me why? That's what the math said. Okay. And if you're going to look at this, that will give you what? 1/2 of 7.37, which is equals to
3.67.
3.67. And the way that you're going to do is minus, we could say 7.37x, and that is equals to the 2x. So the rule that we have, all that are the same is on the same side. So that will become what? 9.37x equals to 3.67. And to get x, you divide both sides by 9.37. So what is x equals to?
.392. 392.
392. Everyone gets the 0.392 plus Now we have the x, but this is not the final answer yet. The final answer is for the HI, it's equals to 2 times x, or 2 times 0.392. And that would be equals to what? 0.799,
8.
0.7884.
Yes.
Now for the I2, which is also equals to the H2, that will be 0.5 minus 0.392. And that would be equals to what? 0.108. Is that 108?
Yes.
So that's the answer. And there's a way to check if it's right. How are we going to check if it's right? Anyone? I'm going to use the values that I have in the expression. 0.784 squared divided by 0.108 squared. And the value should be equals to or close to 54.3. Kindly check. What do you get?
I got 52.7.
So at least it's close there. So I think it's in the rounding up. There's what we call the propagation of error that happens there. But in my notes, it's supposed to be 0.393, the one that I have here.
I got 393.
So in case you get 0.393, so that will be 0.786 squared divided by 0.107 squared. Maybe it will be much closer to the 54.3. Question before I go work on another problem similar to this one.
Professor, what's the unit for
Hmm?
the concentration?
The what?
The unit for the final concentration of the
I told you there's no unit for the K value. So here, if you want to look at the unit, then it's still molarity because it's asking for the concentration. But for the equilibrium constant, there's no unit on it. We're going to see it's just a number here. So there's another problem. It's still utilizing the same problem, but there's a big but. You have an initial concentrations already. So what will happen here? This is what we call the initial concentration. You just follow the table. So how do we do the table? So I can do here the rise. So I have what? H2 plus I2 producing 2HI, right? So what is the initial concentration that we have here? So this is 0.00623. This is 0.00414. And this is 0.0224. And what are the changes? What's the changes that we have here? Anyone?
0.00623 minus X.
No, the changes is just minus X. The changes is where you put your X.
Right.
Okay. How about the HI?
X. Oh, 2x.
So everyone see why is it 2x? Question on that? Question why I put an x minus x here and a plus 2x here? This is minus x because I have only one coefficient for each of the reactant. This is plus, and this is minus because it's a reactant. This is plus because it's a product. So if you're going to look at the equilibrium, all you need to do is bring down everything. 0.00623 minus x, 0.00414 minus x, and 0.0224 plus 2x. Now, before we proceed, because he's going to ask you at equilibrium, before we proceed, can we get the Q value? Can we get the Q value? What do you think? Can we get the Q value here? All you need to do is what? 0.0224 divided by 0.00623 times 0.00414. Oh, shoot. 0.00414. And what do you get? Class, please calculate it on your own. So what is the Q value that we have?
0.0128.
So we have 1.49 times 10 to the negative 2. Did everyone get that? Oh, wait, I think I have missed one. What did I mess up here?
You have to square it.
Very good. So now if I squared it, what is the value of my Q?
I got 14.46. I'm sorry, 19.46.
19.46
46.
or 19.5. So what is the initial K, the K that we have there? 54.3. So it's still going toward what direction? The forward or the backward?
Reverse.
So for the reaction to reach equilibrium, it still need to proceed from left to right. You still need to proceed the forward reaction. Everyone get that? Because of the relationship of Q with respect to Kc, if you ask why. Okay, so I'm trying to just apply the concept of QC value with respect to Kc. So now we solve in the X. So this is where you have this quadratic formula. So you do the same thing as that one, but you put Kc and you're going to put here the value that you have there. And if you're going to have the Kc is equals to what? 54 point. No, not is it 54? Yes, 54.3. Now we need to express this into ax squared plus bx plus c equals to 0. What do you call this?
Quadratic
The quadratic equation.
equation.
Okay. Now, what I'm going to do, and it's up to you to practice, is I'm going to convert this expression to this, an ax squared plus bx plus c, because I don't have the time to do it one by one, because that's more on math than chem. So this is 50.3 x squared plus 0.654x, okay, plus 8.96 times 10 to the negative 4. Everything equals to 0. And what we're going to do, we're going to use the quadratic formula to solve your x. So x is equals to b minus plus or minus b squared minus 4ac divided by 2a. So imagine if you're going to solve it using that quadratic formula. And right now, okay, I have already told you I'm just going to use the perfect square. And if you're not going to listen, I will not be surprised during your exam, you doing this thing. I'm trying to simplify your life, but some students always like this Facebook status known as complicated. Okay, so for the sake of answering the question that we have here, so all we need to do is replace it the value that you have there. So I think we have a negative 0.654 and then plus minus 0.654 squared minus 4, okay, times 50.3 times that one divided by everything divided by 2 times 50.3. And you're going to get 2x value here. So I'm trying to simplify everything, okay? I'm trying to simplify everything because I don't want you to do this in your exam. Maybe by thinking, oh, maybe there's a reason why he didn't really discuss it in details. And because some students, they don't listen. Oh, how did they do that? So I already tried to simplify your thing. We have a perfect square problem. So these are the values that you have. Now the question is, which one is the right one? So you're going to look at the value and compare it with the initial concentration. So you have 0.0114. What do you have here? A 0.00624 and a 0.00414. Remember, this is your x. So what does this mean? If you're going to use this value, this is larger than this one. And you're going to subtract that number with the given number. Does that make sense that it will be the right x? Ask yourself.
You're going to get a negative value.
You're going to get a negative value and it's not possible. So that means this is not the right x. Now the other x is smaller than that. Okay, so it makes more sense compared to that. So all you need to do is subtract each of one. So you have here H2. So that will be 0.00623 minus 0.00156. And then your I2, so that is whatever is the initial concentration of 0.00414 minus 0.00156. And then your H2 or HI, So that is equals to 2 times 0.00156. And you will get there the corresponding concentration. So here you might have what? 0.00467, here 0.00258, and here 0.0255. And if you want to check if they are the right one, you use that number in the setup of this, and the value that you get when you do the calculation should be equal, if not close to 54.3. So question. Before we go on the last part of the chapter, the quiz that you have will just be at the end. We don't have a quiz in the what we call during the break. So we might just have a 10-minute break. So the last part that we have is the so-called Lechaterious Principle. Remember the number game that we have last week? Where did we stop? Where did we stop with the number game last week? You still remember that? Is it on 13 and 27? And you have what? 7, 7? Is that where we end up last time? Now, what if in some instances you add 20 items here? So what will happen? So this now become 47. So remember the exchange, 1/2 of box R goes to box P and 1/4 of box P goes to box R. So 1/2 of 13 is still 7. Now what is 1/4 of 47? Can we say 12? 12, 12, 24 plus 24, 48. So I think it's 12, right? Anyone follow what I mean here?
Yes.
Yes.
You know where I get the 12? Because 1/4 of 47 is around 11 point something. So in that case, so this one will now change because you lose 7, but now you gain 12. So this now will become plus 5, 18. And this one, you lose 12, you gain 7. So this now becomes 42. So what is 1/2 of 18? Anyone?
9.
9. And what is 1/4 of 42? Can we say 11? Because 11 times 4 is 44. So maybe it's around 10 point something. And in that case, this now becomes 20 and this becomes 40. And what do you have here? This becomes 10 and this becomes 10. So what happened? So what is the system that we have here now? Equilibrium. We reach the equilibrium phase. So the plus 20 here represents what? Stress. And again, the 20 items that you have here is not the same as the 20 items here. The 40 items that you have here is not the same as the 40 items here. So we have a system at equilibrium, a stress was applied to it. What the system do is try to relieve the stress until it reach equilibrium again. So that is the concept of the so-called Lechaterious Principle. If an external stress is applied to a system at equilibrium, the system adjusts in such a way that the stress is partially offset as the system reaches a new equilibrium position. So I like to discuss this to you in terms of this one. So the one of the stress that happen here is the changes in equilibrium, and I'm just going to show you here in this figure what happened. So you have a system in equilibrium for the production of the ammonia, and then all of a sudden you add ammonia. So what happened there? So everything now here is at what? Equilibrium. And then all of a sudden you add ammonia there, the concentration of that just increased. So what happened to the ammonia? The ammonia is utilized, so as time it goes down. So which reaction is favored as the concentration of ammonia decreases? Is it the forward or the backward reaction?
Backward.
Backward. Because you added ammonia there, the main mechanism to relieve the stress is to utilize that added material. And to utilize the added material, the equilibrium shifts left. Now, as it shifts to the left, you produce more hydrogen and nitrogen. So usually, if you're going to look at the effect of concentration, anytime you added something in the reactant or in the product, it will favor the reaction that will utilize or use the added material. So if you add something in your product, it will favor the backward reaction. If you add something in the reactant, it will favor the forward reaction. So if you increase the concentration of the products, the equilibrium will shift to the left. If you decrease the concentration of the products, okay, it will shift to the right. So what does it mean? If I decrease one of the product here, the reaction will forwards towards the formation, okay, to replace the species that was removed. So if you decrease the concentration of the products, it favors the forward reaction. If you increase the concentration of the reactant, it will utilize it, so it forward the forward reaction. If you decrease the concentration of the reactants, it favors the formation of replacement of those reactants that was removed. So how do you think they produce ammonia in the industry? Anyone, if you have this reaction? What's the practical application of this Lechaterious principle? What do you think they do so that they will continuously produce ammonia? Anyone?
They keep taking the ammonia away.
Yep. So once the ammonia is formed, you remove it. So if you keep removing the ammonia, what will happen? The reaction will keep producing ammonia. Because you want it to be forward reaction forever. So you make a setup that once the ammonia is produced, you remove it from the system. And in that case, it keeps producing the ammonia. That's the most practical way. Okay? So that's the effect of what we call concentration. So we can look at this also using K value, the QC and the KC. Okay, so you have here at 720 degrees Celsius, the equilibrium constant is 2.37 times 10 to the negative 3 for the production of the ammonia. Now, in a certain experiment, the equilibrium concentration are 0.683, 8.80, and 1.05 molar. Suppose some ammonia is added to the mixture so that its concentration is increased to 3.65. use Lechaterious Principle to predict the shift in direction of the net reaction to reach a new equilibrium. So what is the what we call prediction there? If you're going to add some ammonia,
The new equilibrium will have more of the nitrogen and the hydrogen and less of the ammonia.
so predict the shift when you increase the ammonia.
It will shift to the right, to
Okay,
the left.
shift to the backward, left.
Yes.
You add more of this, so that means it will utilize. Now, how do we prove it? So to prove that it goes there, what should be the value of QC with respect to KC? Will it be equal, less than, or more than KC?
More than.
So we need to calculate the given value that we have here. Okay, so we could say QC is equals to the concentration of NH3. Now, what we do is we're going to change that to 365, okay? You know why we use 365 and not 1.05? Because the 1.05 is the concentration at equilibrium. But what we do is, it's just like this one. See this problem here? So we, the 0.65 is this concentration, but the one that we have now, the 3.65 or the 0.105 is this one. And this one becomes your 3.65. So that means we're still going to utilize whatever is the equilibrium concentration of the other species. Do you follow that? So we use 3.65 squared over 0.683 times 8.8 to the cube. So what do you get? What do you get? What's the QC value that you get? Anyone?
It's my calculation 0.028.
0.028. What's the next one?
62.
6. So you could say 2.86 times 10 to the negative 2. 1, 2.
Okay.
And is it bigger or lower than 2.37 times 10 to the negative 3? What's the relationship between these two values?
It's
Do we
bigger.
meet this relationship?
Yes.
Yes, so that means QC is greater than KC. And that's the proof that the prediction that we have that it's going to go backward is correct. Because based on the QC value, it's larger than the KC value. Question? Before we go to another stress. So the next stress that we have is, we could say, volume and pressure, and they go hand in hand. Okay, what's the relationship that dictates volume and pressure? What gas law is that? Anyone, if you recall Chem 1? What law relates pressure and volume? Anyone?
Charles Law.
Hmm?
Charles Law.
Is it Charles' law? Charles' law is temperature and volume.
Boris Law.
Okay. So Boris' law states that volume is inversely proportional to pressure. The higher the pressure, the lower the volume. The lower the pressure, the higher the volume. Now, this can be a stress if you have, okay, if you have, listen to this, an equal number of moles of gases in the product and the reactant sides. If they have equal number of the products and the reactant side, the changes in volume and pressure will not have any effect. Okay, so what happened? If you're going to increase the pressure, the one that is going to be favored is the one that has the less number, the direction that has the less number of moles of gas. So if I follow it, the one here, if I increase the pressure, which one is favored, forward or backward in this situation here? Anyone? If I have 1 mole of A reacting with 1 mole of B to produce 1 mole of C. So if I increase the pressure, which one is favored? Forward, backward?
It will have no
The forward reaction.
forward.
The forward reaction, because you have only 1 there compared to 2 here. So that would mean side with few moles or fewest mole of gas. Now, if you decrease the pressure, it will be the other way around. Now, in terms of volume, if you increase the volume, that corresponds to a decrease in pressure. So it goes to the side with the most moles of gas. And if you decrease the volume, it sides with the fewest moles of gas. So if you increase the pressure, that results in decreased volume. So the backward reaction, oh no, the forward reaction is favored, at least for this situation. And I have some change, I mean some things here. So it says here, predict the direction of the net reaction in this case as a result of increasing the pressure. So forward, backward. First reaction.
The forward reaction.
So if you have here, you only have 3 here, you don't include this, and you only have 2 here, you don't include this. So the forward reaction is increased. Here, forward, backward. Anyone? Number 2?
Backward reaction.
Backward, because you have your 1, 1, and you only have your 1. So there's 2 here compared to 1 on that one. So you favor the one with the fewest side. And this one?
No change.
2 here, 2 here, so nada. There's no shift in the reaction. There's no change in this one. Now, the other thing that we need to remember also, in addition to this, what we call pressure and volume, is the temperature. But what did you know earlier? What did we said? The K value changes with respect to temperature. Now, in order to look at the changes in the temperature, you have to recall, you still remember the endothermic and exothermic reaction? Because depending if you have an endothermic or exothermic reaction, the changes in the temperature is different in a given system. So for instance, okay, if you increase the temperature, the changes for exothermic reaction is different as that of the endothermic reaction. In an endothermic reaction, where is heat? Okay, so this is the reactant, this is the product. So tell me, where is it in the exothermic reaction and where is it in endothermic reaction? Class, are you still there?
In the exothermic reaction, heat is released.
So it is in the product side. And in an endothermic reaction, heat is absorbed. So it is in the reactant side. Now, to simplify the thing here is treat heat as one of the reactant if you have an endothermic reaction, or a product if you have an exothermic reaction. So what do you think happened to K in the exothermic reaction if you increase the temperature? Will K go up or down? Or what happened if you increase the temperature in an exothermic reaction? Which is favored, the forward or the backward reaction?
The backward reaction.
Because if you increase the temperature, if you have exothermic reaction, you have this here. So the backward reaction is the one that is favored. And what do you think happened to the K value? Since you're going to form more reactants and less products, your K decreases. What is K? Product over reactants. So as you decrease your products and increase your reactants, your K decreases. Make sense? Anyone? Are you still with me? Class. So let's look at it again. You increase the temperature. In an exothermic reaction, where is the heat? Is it in the reactant or the product side? Okay, it is in the product side. So as I told you, consider heat as one of the product. So you have more products there. So which one is favored? The backward or the forward reaction? To those who still don't get it. Since you have more heat there, that means we have more products. So the one that is favored is the backward reaction. And since the backward reaction is favored, that means you're going to have less products and more reactants, resulting in decrease in the K value. Does that make sense? Now, if it's the endothermic reaction, so the one that is increased is the reactant because your heat is in the reactant. So if the reactant is going to be used up, so what will happen here? You have less reactants but more products. So in that case, in an endothermic reaction, if you increase the temperature, your K value increases. Now, if we're going to do it the other way around, where we decrease the temperature, so that means you don't have any heat here. So it will favor the reaction that produces heat. So it will favor the forward reaction. And if it favors the forward reaction, you produce more products and less reactant because you use up your reactants. Hence your K increases. So the same thing in an endothermic reaction, you decrease the temperature, you don't have heat. So it favors the reaction to produce heat, which is the backward reaction. And in a backward reaction, the concentration of your products decreases and the concentration of your reactant increases, which results of your K being decreased. Later, after the break, we will have some example here because I will end up this lecture. Okay, so for instance here, before I go to the last one, what is the reaction? Is this endo or exothermic reaction?
Endo.
Indo.
Okay, it's endo. Usually an exo would have a negative sign. Very good. Okay. So in this reaction, when it is colder, okay, you will see it's less, or we could say lighter in color. And if it's hotter, it is darker in color, because if it's hotter, okay, you form more NO2, which is brown in color. If it's colder, that means lower temperature, okay, you form more of your N2O4. That's why you have a lighter color there in the solution. Now, the last here that we have here is the what we call catalyst. Now, we discussed already what the catalyst is in our previous chapter. It doesn't change the K value. What the catalyst do is just make the reaction reach equilibrium faster, but it does not shift the position of an equilibrium system. It will not have any effect, okay? And what the catalyst do is just lowers the activation energy. So this is what we call uncatalyzed reaction. And this is a catalyzed reaction. So the catalyst is here. So it lowers the activation energy on both forward and backward reaction. And the catalyst does not change the equilibrium constant or shift equilibrium. No effect. Just like if you have the same number of moles of gas and number of moles of gas in the reactant and the product side. And if we summarize this one, although this is not yet the end of the chapter, because I want you to apply it when we resume class later on. So if we're going to look at the stress or the changes that we have, concentration would lead to shift in equilibrium. Okay, it will not change the equilibrium constant. Pressure can shift the equilibrium depending on the moles of gaseous products and reactants. If they're both the same on both sides, it will not have any change. It will not change the equilibrium constant. Volume, okay? It will shift the equilibrium again depending on the relative moles of gaseous products and reactants. It will not change the equilibrium constant. Temperature, it will shift the equilibrium, and at the same time, it will change the equilibrium constant. You see that K decreases, K increases with increase or decrease in temperature. So that's the effect of the temperature. Now, last, catalyst, it will not shift equilibrium and it will not change the equilibrium constant. So question, next, when we go back, I'm going to discuss some of these as an application, so you will know the effect. And then we proceed with chapter 15. So question. Yes, Chinon.
Professor, could you go back to the pressure, because I was confused when you used the equation to explain.
So in the pressure, all you need to do is you look at what side is less. Because if you increase the pressure, what happened to the volume?
Oh, it will decrease.
Okay, so if you increase the pressure, you decrease the volume. So in that case, the one that is favored is the one that has less number of moles side. So between the example that we have here, so this is what? 2 compared to 1. So if you increase the pressure, which also decrease the volume, it will favor towards the formation of the product, because the product has less number of moles compared to the reactant. Now, if you do it the other way, you decrease the pressure, which results in increased volume. So the one that is favored is the one that has more number of moles, which is the reactant side.
So, sorry, for the first one is the forward reaction less favor, right?
Yeah.
Oh.
Because see, sides with fewest moles, is 1 fewer than 2? So 1 is less than 2. So you favor the formation of the one that has only 1. Now for the decrease in pressure, 2 is greater than 1. So you favor the formation of the products. You favor the formation of the reactants over the products when the pressure is low or when you have higher volume. Question? Before we have a break, we resume at 11. We will have an application of all of these by 11, and then we proceed with chapter 15. We don't have a quiz during the break, okay? So we'll resume by 11. So it's 10:49 in my clock. So come back when it is 11. So let's continue. So I told you we're not done yet with the what we call the chapter. So what we're going to do is we're going to apply some problems on this chapter. How are we going to summarize or apply all the summarized stress that we have? So for instance, in this problem here, consider the following equilibrium process between dinitrogen tetrafluoride and nitrogen difluoride. Okay. So you have here N2F4 producing 2NF2 and a delta H that is equals to 38.5 kilojoules per mole. Is this exo or endo?
Endo.
Okay, so this is an endothermic reaction. So let's try to look at what will happen, the changes in the equilibrium. So it's just either forward or shift to the right or backward or shift to the left. The reacting mixture is heated as constant volume. So what will happen? Left, right, shift to the left, shift to the right. Anyone?
Shift to the right.
How about the others? So this is an endothermic reaction. If you're going to heat it, that means the temperature increases. Everybody got that? Next one, some N2F4 gas is removed from the reacting mixture at constant temperature and volume. So that means what happened to this? Increase, decrease. Is the N2F4 increasing or decreasing in this condition?
Decreasing.
Decreasing.
So which one is favored, forward or backward?
Backward.
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 Okay, shift to the left. And then here, the pressure on the reacting mixture is decreased at constant temperature. Pressure, so the pressure here is decreased. So will the forward reaction or the backward reactions favored? Anyone? So this is how many moles do you have here on this side? 1. And then how many moles on the other side? 2. So you increase the pressure. Which one is favored? The formation of the reactant or the formation of the products? Anyone?
Formation of the reactant.
So the backward reaction is the one that favored because you increase the pressure. Oh, wait. Wait, it's not increasing. It's what? It's a decrease in the pressure. It's not increasing. So the one that is favored is the forward reaction. Okay? Because this says it's decrease. So the one that is favored is the one that has more numbers of moles. Last but not the least, a catalyst is added. Catalyst has what?
No effect.
No effect. How are we going to write the K for this reaction? Anyone? How do we write the K for this? This is
NF2 squared.
NF2 squared over
And 2F2.
NF4. So that's what we have for chapter 14. And as I promise you, you will have it in 2 weeks. Is that clear? And then later on, we will discuss more problems so that you will be more familiar with this concept here that we have discussed today. So questions so far? The coverage of your exam on October 30 is until this one, but we have to move on to the next topic because I want my students to be well ahead for their Alex. How are you in Alex? How is everyone in Alex? Okay, Alex is the only thing I want my students to be in Alex is for them to be at least well ahead. It's hard if you're going to be left behind. And I think what's the deadline that you have for tomorrow? Is it already equilibrium? Because the deadline is usually Sunday, am I right? Class, am I right that the deadline is every Sunday?
Yes.
So what's the deadline that you have for this week? Is it equilibrium? Or
It's the end of chapter 13 and beginning of chapter 14.
okay, then at least we're really well ahead. Okay, because the way I try to do it is we're ahead of the lectures, and then the Alex is one way for you to understand more based on the given questions that they have there. So that's the idea. It will be hard for you if the lecture is behind compared to the Alex because you are meeting some terms for the first time in the Alex. Okay. So that's the concept that we have here. If we're done with the one chapter, we proceed to the next one because we also don't know what will happen, especially during this time of uncertainty. At least the uncertainty was already what we call reduced with the vaccine thing. Okay. So we're going to proceed right away with the next chapter, which is not covered in your what we call second exam. But since this is a recording, okay, I also have some problem with the recording. I cannot upload anymore the recording in the Blackboard. I tried to do it the whole week, okay, and it's giving me an error. So what I'm going to do is maybe just post the link there where you can find it in the YouTube. I think that's the best way for you to look at the. I hope to make it available by today. So I think I already used the thing that I need to use because remember all the lectures are posted there. The only one that we don't have recordings there is during the time when we meet in person. Okay, so I'm going to proceed right away with the next one. Okay, so if we're going to look at the next topic that we have, this is acids and bases. Okay, and this is just a continuation of what you have learned from chapter 14, as I've told you. Okay, so this is the start of your K. So what have you what K have you seen so far? KC, KP, right? So here in acid and bases, that K is going to what we call increase in numbers. And as I've told you, the name of the game in this course is where are you with respect to K? If you are DO with the K, are you before K or after K? But after the first exam, it seems all of you are after K. All of you are knockout. Only some are okay. Okay. So that's the thing that we have. That's why I told you chapter 14 is the most important chapter of all. Because what we have discussed in chapter 14 will just be repeated here. Because the system that we have around us are mostly in equilibrium. There's no such thing as one direction reaction. Most of the reactions that we have are attain equilibrium from time to time, if not all the time. So we go with the acids. Acids are around us everywhere. How do they taste? Usually they taste sour. The vinegar, it has the acetic acid. The citruses, okay, they contain citric acid. Some of the citrus fruit can be sweet, but most of them are sour. Okay, some of these citrus fruit that's sweet is because they produce sugar with them. Okay, and usually if you have an acid, it reacts with certain metals to produce nitrogen gas or hydrogen gas. The only exception here are the so-called noble metals. So what are these noble metals? So these are gold, silver, and platinum, or known as the metals that is in jewelry. I don't know if you know it, but in some other countries, they usually have this gold and then they put it in a vinegar, or let's say some of these citruses extract, and they try to prove to their buyer that what they have is pure gold, because if it's not pure gold, it will react. Okay, the acid will react with the metal and produce hydrogen gas. And then the acids can also react with the carbonates and bicarbonates to produce carbon dioxide. So usually what is really produced there is this that will break down to H2O and CO2, the carbonic acid. Now, bases on the other hand, okay, they usually bitter. So if you taste these Tums or antacid, when you have too much to eat, they have a bitter taste. And if you're going to feel them, they will feel a little bit slippery. Okay, and most of the soap are usually that made up this what we call bases. So these are what we call the acids and bases. They are common around us. Most of the food that we eat, are they acidic or basic? Anyone? What can you say about the food that we eat? Are they mostly acidic or basic? What's the food that we eat? Are they basic or acidic? What do you think?
Acidic?
Acidic?
Okay, most of the food that we eat, if I'm going to what we call poll you, they are what we call acidic. That's why if you have too much food to eat, what is the term that we have there? Hyper what? You got hyper acidity because you have too much food to eat. And what do you take if you have hyper acidity? Anyone? You take antacid. Okay. So if we're going to look at the definitions of an acids and base, there are a lot of definitions, and we go it based on the sequence that was provided by the book. So the first definition that we have is the Bronsted acid. In other books, they call it the Bronsted-Lowry acid-base definition. So there are two independent persons. So you have Johannes Bronsted from Denmark and Thomas Lowry from England. They proposed this definition of acid and base. So a Bronsted acid or a Bronsted-Lowry acid is a proton donor, and a Bronsted base is a proton acceptor. Now, this is not new to you because in your Gen Chem 1, there's a discussion about the so-called acid-base reaction. Now, in this definition of our Bronsted acid-base definition, so what happened there is we just have a proton exchange. Acid-base reaction is just proton transfer. So if you're going to look at the protons transfer here, so you're going to lose one of the proton here, which is hydrogen, and it will be obtained by this one, giving you an NH4 plus and an OH minus. They should have an additional hydrogen here. So this one should be like this. So the one that what we call donates the proton, that's the acid, and in this case, that's your water. And the one that accepts the acids, that's your base. Okay. And if you're going to look at this on the other way, since this is a reversible reaction now, this can also what we call serve as your acid, and this serve as your base in the reverse reaction. But before we go on that, okay, there's also an additional term that we have here. So those that accept the hydrogen, when they form, they are what we call the acid part. We call it conjugate acid. Now those that becomes what we call deprotonated, since the hydrogen was donated, okay, that's what we call the conjugate base. So if I ask you, what is the conjugate acid of NH3? What is your answer? Or what is the conjugate base of water? So the conjugate acid of NH3 is NH4. The conjugate base of water is OH minus. Now, what is the conjugate acid of H2O? Because if you're going to look at this, so this is what? NH3, NH4 plus, and then you have H2O, and then OH minus. So if you say conjugate acid, what do you observe? You have more than one H. And if you say conjugate base, you have one less than H. Do you see the thing? So we could say this is the conjugate base of this, and this is the conjugate acid of this one. Now this is OH is the conjugate base of H2O. So what's the conjugate acid of H2O? Anyone? Or maybe when we go later, you might understand more about the conjugating. So someone answer it, no? Okay, but we'll go on later because that's the one that's being asked here. So you're asked here to identify the conjugate acid base pair in the reaction between ammonia and hydrochloric acid. Bronsted-Lowry or Bronsted-Lowry acid base definition is the one that contains the conjugate. What's the word close to conjugate? Anyone? What do you think is the best word or the closest word to conjugate? I'm not sure if you heard the term conjugal. Is that the first term for you to hear that word, that term? Conjugal property. Where do you hear that term? Usually in what?
Connection, like
Huh?
aiding connection.
When you say conjugal property, what does it mean? It's husband and wife. Ownership by husband and wife. So the way that you look at the conjugate acid and the conjugate base pair here is just how they're different with the hydrogen. So which is the acid here and which is the base? Anyone?
Wouldn't the base be NH3?
Okay, so I put the base here. And this one is the acid. Now, what's the partner of NH3? It becomes what? The NH4 plus. And HF becomes F minus. So if this is the base, what do you call this? What is NH4 plus with respect to NH3?
Conjugate acid.
So what separates the two? What's the difference between ammonia and ammonium ion? One has what? Okay, one has an hydrogen additional H plus. Now how about the HF? So this is the acid. So what do we call the the F minus here? Conjugate what? That's your conjugate base. So look at where is the conjugate acid. The conjugate acid is always what? One more or one less hydrogen? And the same thing with the base or conjugal base. Is it one more or one less hydrogen? Okay, so if you have a conjugate acid, it is one more hydrogen compared to what it is in the reactant side. If you have a conjugate base, it is one less hydrogen compared what it is in the reactant side. Are we clear on that? So if I ask you what's the conjugate base of HF, you should be able to say, okay, conjugate base, so that means one less hydrogen. Or what's the conjugate base of NH3? So that means one more hydrogen. That's why if I ask you, what's the conjugate base of water? Or what's the conjugate acid of water? So you should be able to answer a question like that. So this is what? If you're going to look at the conjugate base, so that's one less hydrogen. Now, what about conjugate acid of water?
H3O plus.
H3O plus, very good. Okay. Because the next item that we have here has something to do with the unique properties of water. Now, water undergo this what we call auto-ionization. So what does it mean, auto-ionization? A molecule of water can break down to form H plus and OH minus, or two molecules of water, one of them can give up hydrogen and the other one can accept hydrogen. So if you're going to look at this reaction that we have here, we can have water that can act as an acid and another water that can act as a base. Do you follow me? So which water acts as an acid and which water acts as a base? So an acid, a water that acts on an acid, usually it becomes the conjugate base. And a base, okay, a water that acts as a base, usually it becomes conjugate acid. So what happened? One of the hydrogen in water will be given out. So that acts as an acid. Now, the water that accepts the hydrogen, that acts as a base. Now, the water that gives up the hydrogen, it became the conjugate base because it lost the hydrogen. Okay. Now, the one that accepts the hydrogen, that's the base, it becomes the conjugate acid because it becomes, it has accepted one more hydrogen between the two. Now, what makes this autoionization possible is because water, they can act as an acid and a base. So these are substances known as amphoteric or amphiprotic substances. So when you have amphoteric or amphiprotic substances, they can act either as an acid or a base, depending on what they have or what's the other species that they have. Okay. Now, if we're going to look at the ion product of water, so as I've told you, a molecule of water can dissociate to give you H plus and OH minus. So if you're going to look at the law of mass action, this is what you have. But what's the problem with this expression? What's wrong with this? Anyone?
The liquid was there.
So this one is a constant. Why? Because it's a liquid. So what will happen? You simplify the equation and you have this. And we call this KW. If you're from the KW. Okay. So the KW here, or KW that you have here, we call it the ion product constant. And it's simply the product of the molar concentrations of your H plus and the OH minus ions at a particular temperature. Okay. Now, if you're going to look at this ion product, usually at 25 degrees Celsius, the value that is given to that is this. And depending which one is more, H plus or OH minus, it can tell you whether your solution is acidic, basic, or neutral. So the 1.0 times 10 to the negative 14 just tells you that that's the product of the ions that you have, H plus and OH minus, or H3O plus and OH minus. Now, if they have equal concentration of the H plus or OH minus, you could say the solution is neutral. If H plus is more than the OH minus, then you could say it's acidic. And if it's hydroxide that is more than the H plus, then you could say it is what we call basic. So that's the relationship that you have between H plus or H3O plus with respect to the hydroxide or OH minus. So what connects the two? This number, the KW. So let's try to solve problems. So if you have the concentration of the hydroxide in a certain household ammonia cleaning solution as 0.0025, calculate the concentration of your hydrogen ions. So where do we start? KW equals to H plus times OH minus. And that is equals to KW is 1.0 times 10 to the negative 14, right? You're going to look here, this one. And which one is known between the two? Anyone? So you have here
The OH.
H plus and 0.0025. Now what are we asked for? this concentration. So what do? We divide both sides by and H plus is equals to what? Anyone?
Um, 4.0 times 10 raised to the power minus 12.
4.0 times 10 to the negative 12. So this is based on this relationship. So that means for the third exam, you have to know that relationship.
Professor, just in case, are you going to give us the constant, this 1.0 times 10 to the power 14 in the exam?
As possible, you should know that.
Okay.
Now, the concentration of your hydronium ion, you can use it, okay, in the concept called the pH, a measure of acidity. Now, if you're going to look at the story of the pH, this is something that came out of the industry. What industry do you think gave the concept of the pH? Anyone? This industry, I could say, is the most important industry in the world. It's the industry known as what? Anyone? What do you think?
Is it pharmaceutical?
Pharmaceutical is the most important industry in the world.
They make the most money.
Yeah, but this industry is, if they die, I think population will going to die also.
Is it the food industry?
This is the food industry, okay? And the food where it came out is, we could say, not really one of the most important food. I mean, even without that, you can still survive, okay? So the industry that they have, this is the one that has what we call the beer industry. So there's a company in Denmark known as Carlsberg. So there's a scientist named Sorensen. So he developed a device to look after the best quality of the beer, because Carlsberg odds is Carlsberg, probably the best beer in the world. Okay, so he introduced this concept of pH, where pH is just equals to the negative of log H plus. So this is another one that you need to know in your third exam. Now, what does the pH tells us? So remember the ratio of your H plus with respect to OH minus, the one that is a neutral. So we're in H plus is equals to OH minus, okay? And if you're going to get, what's the concentration of that? Remember, H plus times OH minus is equals to what? KW, right? So that's 1.0 times 10 to the negative 14. So what do you think? How do you think you get the value when H plus is equals to OH minus? So maybe let X equals to this. So how do you get X? What do you do with the what we call value here? So
Find the square.
okay, you get the square root. So if you get the square root of 1.0 times 10 to the negative 14, it gives you this value. So at neutral concentration, both the H plus and the OH minus would have a concentration of 1.0 times 10 to the 7. And it will give you a pH equals to what? 7. Okay. Now, if you have the acidic one, the H plus is more than the OH minus. So you could say anything that is above 1.0 times 10 to the negative 7, it has a pH that is less than 7. And in such cases where you have the basic solution where OH minus is higher than H plus, so that's the instance where the H plus is less than 1.0 times 10 to the negative 7. And then the pH is more than 7. So if you're going to look at the relationship with pH and H plus, it's like this. Or they have what? A seesaw relationship. As the pH increases, the H plus decreases. Or as the pH decreases, the H plus increases. You follow? Everyone follow this concept? So what does it mean? As the concentration of your hydronium ion or H plus increases, your pH will go down. If the concentration of your H plus decreases, your pH will go up. So usually, okay, there are what we call 14 units of pH. So if it's less than 7, it's acidic. It's more than 7, it's basic. If it's equals to 7, it's neutral. Now, you can relate also the pH that you have with POH. Okay, remember, the one that we have here is just with respect to the H plus. But what if we want to do it in terms of POH? Can we do that? Do you think we can get the POH also? Anyone? The answer is yes. You can get POH in terms of the concentration of the OH. You're going to get there the negative log of OH minus. Remember the KW expression that we have, H plus times OH minus is equals to 1.0 times 10 to the negative 14. So what we're going to do, what if we're going to get the log of that one? So we get the log of H plus here, the log of OH minus, and then we get the negative log of 1.0 times 10 to the negative 14, and it will give us 14. So what is negative log of H plus? Anyone? What is negative log of H plus? That's your pH. And the negative log of OH minus, that is your POH. So what does it mean? pH plus POH is just equals to 14. So once you have the pH, you can also get the POH. That's what it means here. Question? If we're going to look at the common fluids and the pH that we have, this is what we have. So as you could see there, most of the juices that we have, they have low pH. I don't know, have you vomited yourself and nothing came out and it's really what? Sour? Gastric juices is the one that's coming out there. And if you watch some movies, you will see some scene when some characters drink something like pesticides to end their life. What do you observe in their mouth? Anyone? Their mouth are usually what? They're foaming. Because what happened, there's some of the gastric juices came out of the body to push whatever chemicals that they have taken. Now what happened? Outside the stomach, that chemicals, which is HCl, the gastric juice, it's not buffered. So what happened? It touch the skin, it will react with the skin, and that's where the foaming or the foam happen. So as you're going to look at here, most of the juices lower pH, most of these cleaning materials are higher pH. Water exposed to air is 5.5, the urine 4.8 to 7.5. Right? Now the body will try to maintain our pH in neutral. This one. So let's try to solve some problems here. Okay. Using the relationship that we have so far. So you're given here, H plus concentration is 3.2 times 10 to the negative 4. After the cork was removed and only half of the wine was consumed. The other half, after it been standing to the air for a month, was found to have hydrogen ion concentration of 1.0 times 10 to the negative 3. So calculate the pH of wine on these two occasions. What happened to the wine? Does it become acidic or does it becomes more basic when you left it standing for a month? So you have here pH equals to negative log 3.2 times 10 to the negative 4. And the other one, you have pH equals to negative log 1.0 times 10 to the negative 3. So what's the answer that you get? Anyone? So what's negative? Okay, anyone?
3.49.
Okay. And the other one? What do you get?
Just 3.
Now, the way that you do the significant figures here, so if you're given the concentration, this is what? How many significant figures this one has? 3.2 and 1.0. You have how many significant figures?
2.
Yeah.
2. Now, if you're given the pH, the one that you, the rule for significant figures there is after the decimal. That's why if you're going to look at this 3.2, I wrote here 3.49 because the only significant figures here is the one after the decimal. Okay. Now, what does this information tells us? That if you're going to drink wine,
Excuse me, Professor.
Yeah.
I got 13.49.
yeah, 3.49.
No, 13.49.
No, it's not 13.9. It's 3.49. Negative log of 3.2 times 10 to the negative 4 is 3.49. You make some wrong calculation there. Everyone who got other than 3.49? Everyone get the 3.49?
Sorry. Yeah, I see my mistakes.
Okay. So if everything that we have learned something from here is if you drink your wine, don't open it. Don't leave it open because it will become more acidic. Okay. Now the next one, the pH of rainwater collected in a certain region of Northeastern America, United States, on was 4.82. So calculate the H plus ion concentration in the water. So all we know is this, pH is equals to negative log H plus. Now, what if the one that is given is the pH and the one that's being asked is this? What will be the formula? What is the inverse of log that you have there? Because what will happen there, you will have what? 4.82 negative log of H plus, right? And then if you're going to want to get the log of H plus, you have here a negative 4.482. So how do you eliminate the log? So that you can only have H plus. Anyone?
You raise it to the power of 10?
Very good. 10 raised to the given pH. If you're going to have it, H plus is just equals to 10 raised to the and what is the answer that you get? What do you get here? Before we call it a day and then we work on a problem.
1.5
1.5
times 10 raised to the power minus 5.
and 10 to the minus 5. Question before we go to our recitation. And then before what we call the 11:30, I'll leave you with the quiz. So what I'm going to do now is maybe solve some problems that we have. I'm trying to open this thing. So let's try to solve some problem. Let's say you have this equation here, or this problem here. So you have your nitrogen and oxygen form nitric oxide. And you're given here the reaction N2 plus O2 producing 2NO. If an equilibrium mixture at 25 degrees Celsius contains 0.040 molar N2 and 0.01 molar O2, what is the concentration of NO in this mixture? And the equilibrium constant is given as 1.0 times 10 to the negative 30. So how do we solve this? Anyone? So we have what? Express it first in Kc. So this is equals to what?
NO squared.
NO squared over
N2 oxygen gas.
So what we're going to do here is we replace it with whatever value that's given. So you're given here 1.0 times 10 to the negative 30 for your Kc. And then you don't know the NO, because that's the one that's being asked. But you have the 0.040 times 0.01. So you rearrange themselves here. So you have NO squared equals to 1.0 times 10 to the negative 30 times 0.040 times 0.01. And all you need to do to get the NO is to get the square root of that, so that you will get the NO value. And what do you get as the NO? Anyone?
Is it 2.0 times 10 to the negative 33?
2.0 times 10 to the negative
33?
How much?
17.
Okay, 17 is the right one. So you multiply the 1.0 times 10 to the negative 30 times 0.040 times 0.01, and then you get the square root of that. Everyone got this? Class?
Yes.
Let me know who's not able to get it.
Well, what I did wrong is I had put the constant, the 1 point times 10, I had put that on the numerator, and then I had put 0.040 and 0.010 at the bottom. But I
Yeah,
know that you cancel it out.
you have to be careful, because I think that's not the correct way to do it.
No, yeah, that's what I noticed I did wrong, because I had gotten an answer, a different answer.
That's why.
So you only square root 1.0 times 10
No,
to the
the main reason why we have to do the square root is because you have an NO squared. And how do
okay.
you eliminate the squared there? So to make it into NO, you have to get the square root of that. So if you do it on this side, you also have to do it on the other side.
Okay.
How about the others? Okay, let's try to do this one. So you have H2HI producing H2 and I2 at 800 Kelvin. The equilibrium constant for this reaction is 0.016. If 0.5 moles of HI is placed in 5 liters plus, what will be the composition of the equilibrium mixture and molarities? So maybe the best thing to do here is do the table. So what's the initial concentration? Is it really 0.5 moles? Anyone?
0 for both HI and H2.
Okay, but is the concentration really 0.5 moles, or you have to do some calculation for that?
It would be 0.5 divided by 5 liters. So that's
Giving you
0.1 moles.
So that's a 0.1, and this is a 0. And then what do you have here in terms of X?
2x.
Okay, so that is a minus 2x, and this is a plus x, and a plus x. Look at the difference of this compared to the example that we have earlier in the class. You swap, but still, if it's the reactant, you subtract it. If it's the product, you add it. Now, if you're going to look at the what we call equilibrium, so this is what 0.1 minus 2x, and this is an x and an x. Now, before we solve for the concentration of each species, what do you think is the Q value? Anyone can determine the Q value?
Q value will be less than 0.016.
Could it be just 0? Because this is what we have. 0 divided by 0.1, or 0 squared over 0.1. Because that's initially what? 0 times 0 over 0.1 squared. So the value that you have there is 0. So that means it moves from the reactant to the product side. Everybody got that? That if you're asked for the Q, it's equals to 0. So that means Q is less than K, because your K is 0.016. Okay, how do we solve this? 0.016 equals to x times x over 0.1 minus 2x squared. Do you follow, class? Everyone follow?
You would take the square root on both sides.
Okay. So what will happen here? So this will become now an x squared over 0.1 minus 2x squared. And this is 0.016. So to simplify this one, we get that. So you end up with what? X over, oops. Now what is the square root of 0.016?
Zero 0.13.
Okay, so the square root of 0.16 is equals to 0.0.
0.13. Oh, yeah.
So it's around 0.0126. I put an extra what we call significant figures so that the error will not be so high. And what do? I distribute this 0.126 with the 0.1 minus 2x. Oh, shoot. And then I have x on one side, right? So by distributing this, so I will get this a 0.0126, and this one will be, how do I get this? 0.252 x, and then I put all x on one side. So this will become 1.252 x, and I have here 0.0126, and then divide both sides by 1.252. So x is around 0.1. Oops. Everybody got that? Analyze.
Wait, Professor, I think I got 0.205.
That should be the answer, the one that I gave you. If you have other answer there, then you have to check. Don't ask me, okay, why you get that number. That means you didn't, what we call, get it right.
Professor, we can't see your work. Thank you.
Now, we're not done yet. What we did here is just the X value. We need to get the concentration of each of them. But as you could see here, so this is an X, this is an X. So we could say the concentration of both the H2 and I2 are the same as the X. And this one would be 0.1 minus 2.01. So I think you will get here around 0.08. Right? And you can still check it. How are we going to check it? Okay, so 0.01 squared divided by 0.08 squared, and that should give you around 0.016. Yep. Well, the way I do it, I just try to what we could do the same side here. Because you don't want to get the so-called quadratic formula in a problem like this one if you have a perfect square. And as I have promised you, that's the type of question that will come out. Question? Maybe I'll try to go with your problem set. Or the so-called exam reviewers that we have. Course material, exam reviewers. So which one do you want to answer here? I would suggest you start doing this problem set or reviewer 2 this week. So if you have any question, we can go over on that next week. Because I want you to be prepared for the second exam. And in historical data that we have, the second exam has the highest overage among the 4 exams that are usually given. So if you're going to look at historical average, you have what, 60 in the first exam. Second exam, students can go as high as 80% average. And then exam 3 is the worst. Now, the answer key for this one is available, and also how to do it is also available. Okay, so if we're going to go here, number 6. So this is just getting for the K value. So if you're going to look at the questions that we have here, where's that? So number 6. So if we're going to look at this, what is the value for the reaction rate constants for the reaction in number 5? So you have here trying to look at the question. Hmm. Time, concentration, time, 0.66. Trying to analyze the thing. So you can choose I'm going to look at the whiteboard. So this is a first order. So that means ln of AT over A initial equals to negative KT. So one that you want here is this one. So based on the stuff that we have here, I can choose 2 points. So let's say 0.66 over 1.22. Then you have negative K and 3 seconds. So what we're going to do, so 0.66 divided by 1.22. Is that 0.5? $60, 1.20. No. What's 0.6?
Yes. Yes.
What's 0.66 divided by 1.22?
0.5.
I don't think it's 0.5 because that's 1.32. So it's less than that. So if you have your calculator, where's my calculator? I don't have calculator right now.
It's 0.54.
0.54. And then you have here negative 3K. So you get whatever value that you have there of ln 0.54 divided by 3, negative 3, and you get there the K. And what do you get? What's the K that you get? Anyone? There, I found the calculator. ln 0.54 divided by negative 3. I get a 0.20 something. Or 0.21. And unfortunately, the closest that you have is the 0.23, right? But the answer key tells us that, what's the answer in the answer key? Number 6, letter D. So I think there was some mistakes here. This should be, if I'm not mistaken, a 0.86. Because if you have an ln 0.86 there over 1.22, so 0.86 divided by 1.22, so you get an 0.740, and if you get the ln of that divided by negative 3, oops, why did I get an error? Why did I get an error?
0.1.
0.116 or 0.12. So I think, yeah, this one, there's an error on that one. So please check, correct that error. But at least that means you are at least going over the problem set, which is really a very good way to do it, okay? You should be doing that. And I can promise you, if you understand those questions in the problem set based on the solution, you're going to survive the course. So question. So I want you to go over these problems that we have next meeting. Okay. So if you have any question, we're going to go over the problem set. Just to prepare you for at least the second exam. Okay. So to tell you frankly, everything is in your hand if you want to do well on the course material. So next week, we're going to continue chapter 15, and then we're going to do review during the recitation hours to prepare you for the exam on 30. So question. So before you leave, I'm just going to open the you have an exam, I mean a quiz. So it's, I think I'm going to put here 25 minutes. Quizzes. Just want to make sure. So I will end this at 1. "25 minutes." So you have all the time that you have, the 25 minutes, because some of you, I don't know why, but the records tells me that you start and submit at least late. Okay. So that's an additional work for me. So it should be open now. You see it? And if ever I will not be able to show the full thing again in the Blackboard, I'm just going to do the link. I have not posted the link yet from our class last week, because I'm trying to do, if I can put the, what we call the recording that we have in the Blackboard as much as possible. I'll try to do it again today. Maybe it will work, hopefully, because I'm thinking that maybe that I utilized already all the available bandwidth that was given to me. That's why it won't attach. So question?